All right, we are now recording. You gonna show off your hair again, Tristan? There you go.
Aw.
The hair. You gonna be the teacher today? We're gonna work on an oxidation and nucleophilic attack problem first. Do you want to help? Let's see if he's still so enthusiastic about OChem when he's in college. All right, so I think what I'm going to go ahead and do is just draw out the problems onto my document camera view. And just do it that way. I'm drawing it out now. I'll switch over. I'm doing it from memory, so it might be a little bit different, but essentially the same problem. Oh, it's backwards. Why is it backwards? More technical difficulties. Here we go. You guys seeing it okay?
Yeah, but you're that's not number one.
Yeah, so one reaction was reacting it with lithium aluminum hydride.
Which question is this?
The structure is different.
Like though, you can pull your PDFs up on your phone.
Good, but I was just the whole thing different about it is the phenyl group. It's not much different, right?
And there is no ketone group. Yeah.
Can you do that?
Yeah.
You can still do that other one too, right? If you wanted to.
Yeah.
But this is fine. Let's do this one. And let me try to fix my focus on my camera real quick before you guys start thinking about what to do with that.
Yeah. You're just missing a phenyl group.
Yeah.
Next to ester.
Advanced. Whatever. Let me try something else. Let me try if I just hold it up. That's probably worse. It's gonna be awkward to do that. Yeah. I might have to edit the video before I post it, right? Anyway, let's do the problem. What do you guys think it's gonna do? This reagent, what does it do?
LAH.
Alcohols. Do one alcohol instead of a ketone on the left, and then the other one is an alcohol too, I think.
Yep, so the thing you want to think about when you have reducing agents is whether or not it's going to be strong enough, or it's like the stronger or weaker one.
Yeah.
Is this the stronger or weaker one that we talked about?
Isn't that the weaker one? Isn't LDA the stronger one?
I think this one is the stronger one. It's really strong.
Yeah.
This is strong.
Yeah, LDA is a base.
Oh, okay.
So
the weaker one was the sodium.
Yeah.
Oh, the NH4 or not NH4.
BH4.
Yeah. Okay. Okay.
Yeah, let's do that one too, just to make sure we're understanding the difference.
Gotcha.
So we'll do that one also after. So the thing about these ones that you want to think about is you want to worry about mass balance. I typically like to account for all the carbons at the end. So we're still missing a carbon.
It's going to be methanol.
Yep, that's correct. All right, and are both groups going to get reduced from the sodium borohydride, do you guys think?
No,
just
only
the ketone.
only the ketone.
Yeah, it's not strong enough for the ester.
Yeah, so we're going to keep all our carbons here. You're going to have an OH now, and we're going to keep this part. Let's do a fun one too while we're at it. So what about if you wanted to say reduce the ester but keep the ketone? How can we do that?
Use DIBAL. DIBAL.
A diol, we need to protect it with a diol.
I'm not sure. What the diol typically does, it allows for reduction of a carboxylic acid to get an aldehyde.
The carbon chain with the OH.
Hang on, I'm hearing a bunch of extra noise. What was that?
The added protecting groups, the ketone, the 2-carbon chain with an alcohol on both ends. Can't remember.
It's ethylene glycol. And then do we need a catalyst for this?
Acid?
ACL.
Yep, H+. And then, so this first step is gonna basically, it's gonna form an acetal from this side,
Yeah.
but it won't react with this side.
Mhm.
And then we can do the reduction and that will preserve the ketone.
Mhm.
So what reducing agent should I use here now?
LAH.
Yep. And then step 3 will just be a deprotection.
Water.
Yep, water or heat. You can also, if you wrote H3O plus and heat, that would also be correct. But water and heat to deprotect. All right. So I believe the other problem that was on that page was methyl Grignard was the other reagent. I also want to mention here too that if you're using a methyl or any kind of Grignard, they typically are implied to have a quench after. Sometimes people won't show it. So usually the quench is done with water or acid.
Mhm.
So what is this going to do? Like what kind of reagent is that?
Gonna attack the ketone and then make an alcohol and then a methyl.
Yep, let's draw it out. So this was a reducing agent for that one. These are all reducing agents.
Yeah.
And then this is basically a strong nucleophile. I like to think about it. And we have 2 electrophilic sites here.
It won't attack the ester though,
Will it?
right? Oh, it does it twice.
Yep, it does. Yeah, that's a throwback from earlier in the semester, right?
Yeah. I remember. It does.
Yeah, so you're going to get nucleophilic attack on the ketone. It's going to do a general addition of a methyl group. And then for the ester group, it's going to put it on there twice.
Yeah.
So you typically get, from an ester, you get a tertiary alcohol from this.
Mhm.
So let's go ahead and draw that out. So we're going to have the extra methyl over here, OH. And then we're going to have, what, OH, and then methyl. Like so.
Do you need to quench it with water to get alcohol?
Yeah. If you were trying to show the product that didn't have the quench, you would just basically show the alkoxides, the O minuses.
Mm. But
like I was saying, that it's usually implied to be a quench. So that's the product you want to draw. All right.
Will we get points for saying it's implied?
On our test, we had to put O- for sure.
Yeah,
With
that's what I'm
Professor
saying.
Yeah.
I want to divert to Professor Hammond on that question. Do they have to show the quench?
If it's a synthesis problem, usually I'd have them do a double arrow and put the quench step after, unless if it was my final problem like these, I'd expect them to have the O- at the end. But yeah.
Okay.
But you're right, a lot of the homework problems assume quenching. Yes, I try to always remember to include it.
Okay. I would just be safe. Yeah, if you want to show the quench product, just write it in.
Okay.
All right, the next one here was an anhydride.
Yeah.
So I always encourage my students to shorthand benzenes at a pH, unless they're part of the reaction. They're basically going to be R groups here. So we have that. And then let's just do it this way. So the first question had reacting with H3O+. And then the second one had it reacting with Lithium aluminum hydride, LAH.
Yeah.
So what is the first one going to do?
Still draw.
Make carboxylic acid.
Hydrolysis?
Yep.
H3O plus.
So
And
we get benzoic acid?
yeah,
Yeah, but both sides will be a benzoic acid.
because it cleaves it, right? Like,
Yeah.
Yeah.
okay.
Yeah, so basically you're going to get an OH on both sides here, and since both sides are the same,
Yeah.
then it'll be the same.
Okay.
So benzoic acid.
Can we just put a 2 in front of that instead of like drawing plus?
You could. All right, what is the LAH going to do?
It's going to reduce those ketones to alcohol.
Like that? What you get that? So when you're
Yeah.
writing out the answers to these, I highly recommend you always keep in mind your carbon count. You don't want to lose carbons here.
Okay.
So I'm thinking that if I gave this question on a test, a common wrong answer would probably be phenol, where we actually have benzyl alcohol instead.
Right.
All right.
That was easy.
Yeah.
Does it have 2 of the same products, or would there be because of the oxygen in the middle, would you get 2 different products?
Yeah, so each side would be a product. So both sides happen to be the same here. All right. So do you guys want to keep working through this worksheet, or you want to just do, because there's a lot on here. I think I'm going to pick and choose instead of doing them all.
Yeah, just pick and choose. Just tell us which ones you're doing.
Okay. What about there's an amide one. I think it looks like it's J that I'm looking at.
Same worksheet?
The same worksheet. I just pulled down.
Oh, yeah.
Yeah, it has a LAH on one side and acid on the other. I'm writing it out. And then double bond O. And then I'm just going to do it this way for the sake of the video. All right, so the first one is a reducing agent, and the second is acid. So does LAH work on amides?
No?
I think so, yes.
Yeah.
It does.
Yes.
Does everyone say all of the answers?
Yes, no, maybe. 12.
It does, I think. Does that
I think it turned it to a NH2.
Yeah, I think so.
Yeah.
I'm not seeing any examples that we've done in our lecture with that.
What does Professor Hammond think? Does LAH work with amides?
Lithium aluminum hydride goes after every single carbonyl functional group without exception and reduces them down. The nitrogen will be the only thing left in this case. So lithium aluminum hydride attacks everything. And I think I did an example 1 on my notes, but yeah, it'll make an amine where the oxygen will be 2 hydrogens.
Okay.
What about this one? What do you guys think?
Wouldn't it reduce
hydrolysis?
carboxylic acid, wouldn't it?
Yeah.
With heat, yeah.
I'm adding this in here.
Carboxylic
That
acid.
wasn't on the worksheet, but I would add that in there because these are pretty unreactive.
Mhm.
So you need some extra energy to get it to work. So yeah, we're gonna get the carboxylic acid, and then what about the rest of the carbons?
You're gonna have 1, 2.
It's
You would have like
So
two
make an amine.
groups, right?
It's
Don't you add
NH2
the
plus.
hydrogen to the nitrogen?
Yeah. Nailed it.
Awesome.
Should there be a positive charge on the nitrogen since it's in the acidic condition?
Good catch.
Yeah, I think it
Yes,
could be.
yes.
Yeah.
Good.
Good catch. All right, let's take a look. And if there's any in particular you guys want to work on, let me know. We can work on it. But I was thinking we can do the 2 problems down. It has a acid halide with a copper lithium and a Grignard.
Yeah.
Why are there 2 H's on that N in the acid version?
What
the
happens
product.
first in all reactions?
Acid base.
Yeah, it's acid base.
Everyone have an acid base.
All right, so we have this. I did a little bit of shorthanding. And then we have this weird looking reagent. Maybe you guys remember it.
Cuprate.
Cuprate.
And then we have this one. So one thing in general you can remember is that if typically if you have these reagents that have a metal in them, these are your organometallic compounds. They're typically strong nucleophiles in many cases. But are they the same? Are they different? Or are they similar? Like what's the difference here?
Cuprate only at one time, I think, like 1 carbon.
And cuprates don't attack carbonyls, right?
Yeah.
Is that what you guys are thinking?
But like
Yeah.
in the presence of a halogen, right? Oh, there's no. Okay, yeah. Yeah.
And what about the next one? What do you guys think?
It's at 2 times
Yeah, Grignard
Yeah.
the 2 carbon there. And then make
It's the same
alcohol.
as esters with Grignards, they attack twice. On acid halides.
Yeah, so I'm adding. It bothers me not having the quench on there, so I'm adding the quench in. I'm being realistic here. Like you wouldn't stop at just that. Not usually anyway, because typically in your workup when you're doing your purification, you would quench it before it goes into a set funnel. All right, not too bad. So what were these called again? They were the cuprates, right? Or cuprate or Gilman reagents, depending on what kind of book you're using or who's talking about it. All right, there's one more on this worksheet I wanted to work on. It's the one right below it. There's another amide one right below it.
Mhm.
All right. This compound and the first reagent was POCl3 and pyridine. Did we learn about pyridine as a solvent or a reagent at any point?
Yeah. Do I remember it?
Like,
Yeah.
is it a reagent? Is it a solvent? Is it both? What is the role of pyridine?
Solvent.
Is there a catalyst?
I've only seen it as a solvent. I don't know what else. Could it be? Could it be a reagent?
Wait, the POCl3, isn't that the elimination of alcohols and it makes a double bond?
Or does it make a nitrile?
Makes a nitrile.
Oh yeah.
Yeah, I don't think I covered this one in our stream that we did during the enolates, but
Yeah.
I think it's in Hammond's notes for this one. If you went through Hammond's notes.
No.
That's basically what you get.
Would it eliminate alcohols? Because I remember reading in the book it would eliminate alcohols.
It's like SOCl2. It swaps oxygens for chlorides. And in this particular case, when it swaps the oxygen for the chloride, the nitrogen double bonds down and then triple bonds down to make a nitrile.
Okay.
So,
Yeah, the next one should be pretty easy for you guys by now. It's like the last one. But there we go.
Yeah. So couldn't we do the same thing, like after it turns into the nitrile, couldn't we hit it with the hydronium and then it would turn it into the same thing, but without the NH4 part?
So you're thinking like
you could hydrolyze it to carboxylic acid, yes.
Yeah. Okay. So it would basically go to the same thing. It's just extra step.
No, it's just making a nitrile. This is one of the special ways to make a nitrile.
You know, I have barely enough room here to write these products out. So like we went over, you should have gone over acid and base conditions.
Yeah.
For this reaction.
Well, that would just turn into a carboxylate.
Yeah. So basically it's these in base conditions.
Yeah.
So then O- and then ammonia.
Yeah.
And we were actually supposed to do this one in lab. This one right here. I still need to do the write-up for that one, I think, for the online labs.
Could you possibly do the mechanism for that first one?
Which one? This one?
Yeah.
Yeah.
No. I mean, we could, but yeah, we're not going to test on that.
Oh.
All right. So do
You
you
said-
guys have any general questions about the carboxylic acids and derivatives before we change gears? I know we didn't do all the reactions, but I think we hit a lot of them.
Professor Mord, I can quickly kind of talk through the mechanism on the first one.
Okay.
Sadly, my picture shows up and you won't be able to see it. So if you look at the double bond oxygen, one of the things phosphorus does is it grabs onto it and makes it so the chloride can add to the nucleophilic carbon. Chloride and the oxygen are now both leaving groups, so the lone pair of the nitrogen will start to double bond and then triple bond back to kick both of them out and leave you a carbon nitrogen double bond while the solvent picks up the hydrogen. I don't know if that makes any sense, but basically the role of phosphorus is to pull the oxygen right off. Does that help or not?
Yes, thank you.
All right.
So on that, then what are the other side products other than the nitrile?
You don't have to worry about it, but the quench ends up making phosphorus acid or phosphoric acid as a combination. And but that's basically, we don't worry about the inorganic parts.
Okay.
So SOCl2 is going to react the same, similar to POCl3?
Yes, exactly the same.
Okay.
It's, and the side product there would be sulfur dioxide.
Okay.
So they're added in there.
Or PBr3.
What about P4O10?
Also the same.
There's so many.
P4O10 is a super desiccating agent. It basically, when you see it, think about removing H2O out of your molecule.
Mm.
Do you guys want to switch gears to doing the different worksheet, the ester and anhydrides one?
Sure.
Well, we did some of it already, it looks like, actually. Yeah, we've done a couple of these. I actually want to look at the stuff at the bottom of the page. So I'm looking at the esters and anhydrides worksheet. There's 4 problems on the bottom for O, P, Q, and R. I think those ones.
Mm-hmm.
A lot of the earlier ones, we did something like them already. Let me go ahead and draw this next one. So then, oops. OCH3. All right, and this one has it reacting with a secondary amine, it looks like.
So wouldn't that just replace the ester, like the OCH3 part, with that whole piece, aside from the H? It would like.
So what are more reactive? Are esters or amides more reactive?
Esters.
Esters.
I guess the other question would be, is this nucleophilic enough? Do you need a catalyst? Anything like that?
Acid catalyst, right? No?
Do we need one?
I don't think so.
I was like, I don't think we need one.
One thing I like to think of when doing these problems is if this is actually going to work or not, because these are all in equilibrium.
Mm-hmm.
But one of the deciding factors is what is the nucleophile on both sides of the reaction. So like the leaving group here would have been this, ethanol. That. So looking at like this nucleophile versus this nucleophile, you can use that to kind of help predict equilibria, but probably wouldn't have that on the test. The other thing I like to think about when doing these kind of problems.
Didn't we have like amides are like the least reactive between the groups?
Yeah. All right.
You're saying the equilibrium is all the way to the left in this one, basically.
The next one has a carboxylic acid, and what are the reagents to make this a anhydride? I think it's gonna take more than one step.
Okay.
And acyl halide?
Yeah, that's right. So remember during the stream, I mentioned how typically you don't want to use a carboxylic acid as your starting point because you might have acid-base problems, it might not be reactive enough, all those kind of situations. So it's
Could we do like SOCl2 and turn that into a chlorine?
yeah, that's what she said, acid halide.
Oh, okay.
So I was just saying, I was just recapping that it's better to do this conversion first because this makes a great leading group.
And then we would need a carboxylate though, wouldn't we?
Yeah.
To do that?
And then I would just use the salt of it.
Okay.
So the sodium salt. There you go.
So for this one, can we just use P4O10 and then use the same molecule? Like dehydration, something.
What does Hammond think?
Sorry, I forgot to unmute. If the two sides of the anhydride are identical, you can use a desiccating reagent like P4O10. But if you want them different, you got to go through the acid halide. So, does that help?
Yeah.
Yeah.
All right, so we have these last two here. There are some ester reactions. Let's do the straightforward one first. This reaction had a name also that you might want to remember.
Saponification?
Yep, that's right.
Okay.
So in OChem, we call it saponification. In biochem, we call it hydrolysis.
Because okay.
So one of the things that I personally look for when I grade problems like this one is I'll make sure that you have the correct acid-base form of it. So since we have a carboxylic acid here, it's in base, you want to show it deprotonated.
Right.
And then I'll usually show like whatever the alcohol is, the leaving group, protonated.
That's
We don't
2
want
carbons?
It's 2 carbons, yeah.
carbons.
That's going to ethanol.
Nothing gets by these people.
Yeah.
I harp on carbon counting. You guys are actually carbon counting. I love it.
Because we get roasted when we don't have carbons. Impossible.
Who would do that? So I want to make this one a little bit more challenging. So like, if I gave this one in a test, I would put side branches on it too. This is the kind of stuff that I do. I'm just going to go ahead and add this on there for fun.
Wouldn't that break that up into like an alcohol? It would break the cyclic compound.
Yeah, it's going to break it right here.
Yeah.
So 2 things here. You need to make sure you get your right functional groups in there. And you also need to account for carbons.
Yeah.
So I like to number. So we're going to have number it this way. That's going to be the longest chain that I just numbered. Wait, it'll be, fix my numbering here.
Would it make one of those into an alcohol and the other into an aldehyde? Or not an aldehyde, because there's not 2 ketones. Just kidding. Just kidding. Ignore me.
So then after I have the longest carbon chain and identifying where it's breaking at, I'll just draw a straight chain.
Just a comment on Crystal's question. You cannot turn an acid into an aldehyde without a reducing agent.
Yeah.
Or any acid derivative. So esters will stay an acid derivative.
If you had used like Dibol and water, then you could have.
All right, so is carbon 1 going to be an alcohol or an acid?
Acid.
An acid.
An acid minus.
Acid, yeah.
Oh yeah. No. Oh, yeah.
And then we're getting an acid and an alcohol, and so notice here at carbon 4.
Yeah.
That's where the OH is at.
Yeah.
And then our missing groups, we have a methyl at carbon 3.
Yep.
And then I think that's it. Like I said, if I get this on a test, that's how I would do that one. I wouldn't have it be just a ring like that. I would put branches on it too. And I'm pretty sure Hammond would also. Yeah, see? Yeah. All right. Let's take a look at the enolates. This is probably the most challenging page, so we probably should do a few out of here.
Okay.
I'm actually going to draw this one out. I'm just doing the first problem on the enolates page. If you draw it out, it looks like a crab. You see it? A crab.
Yeah.
Oops.
Stop making fun of me. Yeah, so we went over this stuff here. We went over this reaction scheme that they're showing here.
Yeah.
So I just wanted to talk through or see if you guys understand what's happening at each step. So the first step there is
attacking the alpha carbon, right? Between the 2 ketones or esters, sorry.
Yeah, so the question I have for you here is why didn't they just use hydroxide for that first step? make the enolate.
Because the ethanol is attached to the oxygen, so you want to do the same. You want to match it.
Yeah.
Has to be similar to the ester.
Yes. So the reason why is because you have the possibility of acyl substitution
Yeah.
as a side product. And if that does happen, you get the same thing back. So if you use hydroxide here, you would just do a saponification and you would get the diacid out of this.
Right.
So to make sure you're actually getting an enolate, we'll do this. So I'm gonna just write here acid base, enolate. And then what is the next step doing?
So wouldn't we do that like multiple times so that it would become a good leaving group, like the iodine?
Say what?
Or would it just attach once?
Okay, the negative charge attacks to the carbon and then iodine will leave.
It's like an SN2.
SN2.
Yeah.
Yep.
Yeah. The enolates can do an SN2 on a good primary leaving group. It's basically the rules of SN2 apply in this case.
Gotcha.
Sometimes people also use a multiple mole equivalents here. But they're only showing it once, so I'm going to put it on there once. So then the last part here is doing 2 reactions.
It's like the workup part, right?
Yeah. So what's happening?
Decarboxylation. Saponification first and then decarboxylation.
Yep. So I'm actually, if you're having a hard time with that, I recommend just drawing it out stepwise. So I would draw the diacid first, like this. And then you could just count carbons here. So 1, 2, 3, 4. That's going to be our straight chain. And then this is our CO2. So 1, 2, 3, 4, and then CO2. Final answer. So the kind of thing you would have on a multiple choice test would be like, if this is on a multiple choice test, you would basically have a bunch of different acids to choose from for your product. So you'd have to make sure you get your carbon count right. And what I essentially think of is for like the going from here to final answer is I think about what the R group is that we're attaching, and it's just coming off of the alpha here. So like your this is like going to be your final product, like this piece right here, and then whatever this is coming off. That's what this is. I'm just thinking for time wise, you don't want to have to draw all this out on a multiple choice test if you're being timed. You know what I mean?
Okay.
So you want to be able to a way to quickly get to answers. So again, we had a saponification.
So these are like the malonic ester things, right?
Yeah, is this malonic or acetoacetic? Which one is it?
Malonic.
It is malonic.
Yep. Oops. And this was malonic ester. All right. So taking a look at the worksheet again, looks like the next one is like an acetoacetic version. We also have the bromination stuff we can do. Yeah, let's just do the bromination one first. That one's probably the easier one out of the two.
So basically, and C squared, for that we'll need to know that.
Well, is this a bridge mechanism?
This reagent is so cool. noticing on this worksheet, they're using the acetic acid as a way to make enols. That's what I'm thinking they're trying to do. I believe in class we showed with the hydroxide instead. But what you could show is with instead of hydroxide, this reacts with H+, and look at the enol from this. And then that's your nucleophile. If you compare it to what we did in class, instead of having an enol, we had an enolate. That's the main difference.
If there was a hydrogen on the right side carbon, on the right side sort of alpha carbon, would that one be where the double bond would form?
Yeah, I would go by most substituted here, but we can't do that on this one here because there's no H's there for the tautomerism.
Got it.
Oh, I see what you're saying. Okay.
What does the bromine do?
Addition?
It adds to the alpha carbon, right?
Is it addition or substitution? Final product.
Oh, no, it's not addition.
Because this is like the sort of like the form reactions, right?
Yes.
Oh, okay.
Yes.
So you want to be careful on these. That's not a true alkene, so you don't want to think like addition of Br2 like we saw last semester. You're doing alpha carbon chemistry here. I'm thinking of my multiple choice question that I would put the bromine addition, like the Br2 adding to both, as a choice. But I guess I'm evil like that.
Professor, I'm a little bit confused here. So there is no deprotonation of alpha carbon here? We don't have any base to deprotonate.
I was showing that this worksheet's using an alternative way to make the enols.
Oh, okay.
Yeah, in class we use the base, but you can also use acid.
Wouldn't the bromine add multiple times though, not just once?
Typically, they'll specify how many mole equivalents are being used.
Oh, okay.
All right, so I'm just looking at C for the next one.
Yeah. Isn't this is basically the same as the first one?
Well, we have a ring now too to deal with, and it's a little bit different. I think it's worth working through. All right, that one. What do you guys think? Like, are we gonna get an enolate from this? Start.
No. Yeah, no, I don't think so. No.
So alpha carbons, the double alpha carbon gets deprotonated.
Well, yeah, because then that would attack the CHI, and that would be an SN2 again. I would leave. I mean, it basically is the same idea as number one, you just don't have the enolate.
So that?
Yes.
And then what happens after that?
And then you do saponification and decarboxylation. And it's going to be only methyl group substitute on your ring.
So I'm right here. I think the next part is probably the tricky part of the drawing, the decarboxylated product now.
Oh.
Where are they going to break at? Like, is this ring going to open? Is it going to be a straight chain? Are we still going to have the ring at the end?
Yeah, that tertiary carbon or quaternary carbon between that and the carbonyl, is it going to break there?
Here?
To the left.
This one?
Yeah.
No.
No, I think it breaks next to the carboxylic acid, right?
Yeah. Yeah, that part.
Yep. Yeah, so if you actually compare it to the other one, we did this, I think we didn't have like this ring part here.
Yeah.
We basically had like a ketone and then whatever R was attached.
Because it should just be a methyl group there.
Yeah.
Right?
Yeah, there will be only a methyl.
Yep. And then
got it.
Carbon counts, right?
You scoot it over a little. There you go.
Get our carbon counts in.
Does it always break there next to the carboxylic acid or next to the acid?
Yeah, so so basically, if you have a ketone with a carboxylic acid in the alpha position, it can decarboxylate. And I think the other like special case of this I showed you guys was, I think we did the THC example where you had that basically.
Yeah.
This can also decarboxylate. Because this can tautomerize to look like that.
Nice.
All right. This is gonna be a fun test, guys. I can't wait. Are you guys feeling enthusiastic also?
No.
Yeah. Can you do N?
N? I don't think we ever covered that reagent.
I know. That's why I said, can you do N? I was like, what the hell is that?
I'll put Hammond on the spot for this one. Oops. Do it again.
Oh, he's getting something real quick. He's getting serious.
All right, so the first step was LDA and THF. And then second step was pH, the selenium. I don't know what that does.
Nice.
We'll find out together. I'm going to divert to Professor Hammond on that one. I know the first part's going to give us the deprotonation.
Deprotonation, yeah.
Okay. It's sad when you can't see James's Professor Moore's problem. Can you click the screen share button on yours, Professor Moore?
What?
Okay. The selenium bromide. Yeah, if you click your share screen little green arrow underneath your Zoom, then they won't see me. They'll see the picture. Does that make sense?
We can see his picture. We can
Okay.
yeah.
We're on your screen right now.
Okay. Anyway, selenium bromide, the enolate S does an SN2 and attaches to the selenium. Kind of like instead of attaching to the carbon you did on the first problem. So now you have the selenium attached on the alpha position. And then if it undergoes an oxidation, then the selenium oxide with hydrogen peroxide will undergo an elimination that usually gives you the anti-Zaceps product, also a Hofmann elimination. So this is basically one of the Hofmann elimination.
Do we have the bromine in here still?
So the bromine gets kicked out and the enolate attaches to the selenium.
Like that?
Like that. And then when you oxidize the selenium with hydrogen peroxide, it then is all set up to do an elimination. So you end up with an alpha beta conjugated system.
Oh.
I kind of skipped that part of my notes because it almost doesn't show up anymore on the final exam. But this is one of those ones that competes with the Hofmann when he does the quaternary amines. We haven't done amines yet, have we?
Alpha, beta.
Unsaturated.
Right.
I don't know how now.
Yeah. I'm going to try to draw.
I don't see any aldols in here.
I was gonna say this is like the aldol eliminate reaction.
It's similar.
Yeah, I'm gonna have to make up some other problems outside of this because there are certain types that I wanted to do that aren't in here. But I'm getting ahead of myself here. I was thinking I wanted to take a look at probably O. Yeah, let's do O.
Okay.
So we have this compound, and then LDA, THF, and was that, and then another equivalent of LDA after that. So the thing is right here, so we have a base here, we have an electrophile that's primary, that's set up for SN2. So enolate goes there, or you could choose the other side too because both sides are equivalent. And while I'm thinking about it, if this were asymmetric, how would you choose which side the negative charge went to? Why do you think?
Let's substitute?
Yeah. Yep. Less substituted. So here we're going to get that 3 carbon fragment. 1, 2, 3, and then bromine. And then effectively what the other LDA is going to do is going to make an enolate here, and then they're going to connect from this carbon to this carbon. So I'm going to number the steps here. So this was step 1, 2, step 3. So enolate there. And then intramolecular SN2. And then the moment of truth, the carbon count at the end. How big is that ring that forms?
6 member.
6 member.
Yeah. So I'm just going to add the bottom portion here. That.
Pros at counting our carbon.
I would have figured if you drew a molecule that looked like it was shrugging, you would guess correctly on this one. It's kind of shrugging. Okay. Yeah, so I'm thinking we need to do some aldol, and we also need to do some conjugate versus simple addition.
Professor Mord,
Yeah.
take your F and change step number 2 to be like benzaldehyde or acetaldehyde.
This one?
No, on your worksheet, the F problem F.
S?
F as in Frank.
Okay.
And just change step number 2 to be an aldehyde of some sort, like benzaldehyde.
Okay,
or,
yeah, I get what you're saying.
Oh, okay.
and then also on F, switch the base from LDA to sodium ethoxide.
Okay. Yeah, that's a good one. All right. So so we're looking at the structure that's in F. One, two. And then step 2 will be just benzaldehyde. And then we can change it to be NaOET and the same. And I want to draw the self-aldol on this one too.
Is that benzaldehyde? Is that what that is?
Yeah.
Okay.
Yeah, there should be enough aldol practice, I think.
What's that last one?
LDA, then it says self-aldol.
Oh. Oh, that's just when it adds with itself, right? It's just
Correct.
another, okay.
So the main difference between, so like the first two here, you got to think about which base is being used, and then which H is going to deprotonate before you proceed.
Yeah.
How long do you guys want to run this for? I wasn't sure how long you guys wanted to go for.
This is fun. What time is it? Oh, I don't have SI until 2:30, so I don't care when everybody else wants to. Whatever.
Well, yeah, I was thinking like work through these aldol problems, and we can do like a Michael edition.
Yeah.
Will we be able to do one Hofmann degradation?
You said Hofmann degradation?
Yeah.
Don't worry about that until the next chapter.
Okay.
That's part of the amines chapter, and we're saving that for the next exam.
Okay.
Yeah, 'cause I don't think we covered that yet, did we, Mo?
No, it's amines.
Yeah, it was on the test that we have.
Professor Mord, my practice exam had questions from the amines chapter. Everybody save those for the next exam.
Okay.
Okay. Oh, perfect.
Yeah, so it seems like what we're going with is I'm using Hammond's note, but we're going in my order. This is what I know, so.
Okay, so we're using LDA and THF.
Yes.
Oh, so this is what you're saying, which does it attack, like between like the most substituted versus like least substituted?
Yep.
Yeah, it would be less substituted.
Yeah.
And so the
I I think the first step in a problem like this is to even recognize that it's an aldol, because there's so much stuff overlapping now.
Uh-huh.
I think the tell on that is probably the fact that we have like an aldehyde and a ketone. That's typically how they're done.
We have an aldehyde.
Yeah, we have an aldehyde and a ketone.
Oh, okay, I see what you're saying.
So to predict if you want to be quick about predicting products for aldols, it's basically your electrophile in the reaction. Instead of having double bond O, it's gonna be double bond to whatever alpha carbon is. So.
Oh, okay.
I do recommend drawing through it, but if you want to just predict the product quickly, it's just this goes instead of double bond O, it's double bond to alpha carbon.
Oh, okay.
The tricky part on the next one, you're not going to be able to get the elimination step on this one, I don't think.
Yeah.
Let me fix the way that I drew that. All right, so it's going to have a bond from here to this carbon.
Mm-hmm.
And then we have our OH, and then our benzene. And notice here, we don't have the H over here to do the elimination, so the reaction stops at the beta ketone, beta hydroxyketone. And once again, it's because we don't have any H's here. All right. Get it all on the page there. There. Ugh. All right, so take a look at the next one here. So saying self-aldol. So just like I was saying with this one over here, instead of having it double bond O, it'll have double bond to alpha carbon. So what I'm going to do for this part here is just basically redraw this and then have it attach right there. What is that, 4 carbons? 1, 2, 3, 4, and then if it helps you guys out, I recommend if you're having trouble seeing it, to draw the new bond in a different color. Then I think it kind of stands out then what's happening. And let me go back and do that with this one too. All right.
So that is trans.
Say what?
That is trans. Like if you were to name that, like if it said name it.
Yeah, I kind of default to the most stable alkene for these. So yeah, it's trans.
Okay.
I guess you can make arguments for the cis product, but I'm betting this one will be more dominant. All right, so I'm thinking we need to do a Michael addition problem. We probably should do a Claisen as well, right? I'm thinking we didn't do a Claisen yet, have we?
Yeah. No.
All right, and just like typical exam, we'll put expert groups on there for fun. And my students already know that what I think is fun and what they think is fun are two different things. So I guess we can use this one and do a couple of different things with it.
Does anyone know which lecture Michael was in?
That was the enolate lecture, I believe.
I know that.
Wait, what, the enolates? Hang on, I can look at my YouTube.
I don't think it was. I think it was the carboxylic acid one. Because that's me in it.
Yeah, enolates part 2 of 2. I can get you a link in the Discord.
No, I just need to find it. But thank you.
Yeah, it's that one that I did where the audio was out of sync.
Oh, okay. Oh,
You're looking at your notes. It's immediately before Aldo reaction.
Oh, okay. I see it. Thank you.
You're welcome.
And that's only if the enolate is the nucleophile. Then we use Michael addition, right?
I'll put a couple reagents up here. We can see what we do. A couple. So we can say and I guess the other one. Yeah, let's try these 4.
Okay.
I'm gonna add to the first one just because I like adding stuff. Here we go.
Oh, I remember this one. Okay.
If you didn't add that H3O plus, would it just be the enolate product? Or would it tautomerize? I don't know.
But we usually show the tautomerized product anyway, even after that first step. This would likely be in water. Although, I guess you could do it in, probably do it in ether as well. But yeah, so let me just draw these out. So the thing is about your nucleophile, you want to think about whether or not it's going to do a simple or a conjugate addition.
It's a conjugate addition.
Yeah, this is so it's gonna the way these are gonna work out. It's gonna be
weak.
Weak nucleophile.
Yeah. Wrote that list down from the lecture.
Simple. Okay.
Yeah.
All right. So when you have a conjugate addition, we did go over the mechanism for this, but you first get the enolate product, but then you get tautomerism to the ketone back. So
We
you
did
essentially
go over this.
do what?
We did the mechanism for this.
Yeah. We did.
Yeah.
So essentially what's going to happen is you're going to get, you can kind of think of it like an anti-mark addition. I'm trying to keep it, how to keep it straight in your head. But it's kind of doing an anti-mark to this double bond or further, or beta position. You can think of it that way.
Yeah.
However, but, and these ones are going to do simple additions. This next one. We actually went over this one during the aldehyde ketones chapter. That's the hydrate.
Could we have, okay, so where did the double bond go on the first, oh, the top one? Shouldn't that be an alcohol with a double bond there? And then like, I mean, it would be an alcohol in the middle, but there's a double bond missing on the top one.
Is there?
Why would the double bond not, I'm just like looking at our examples from when we formed the enolate.
It's automerized.
Oh, it's because it turned O negative and then it, oh my God, okay, yeah, never mind.
For the top one, would it go like hydrolysis of nitrile to carboxylic acid?
Yeah, so that's what the second step is for. So this is the part for the first step, and then this is step 1, and then step 2.
Yeah.
That.
Mm.
And then what about the third one? What is that going to put and where?
An ethyl group.
1, 2. Oh yeah, it is an ethyl.
Oh, the ethyl, yeah.
And then what about the Grignard reagent?
That's a strong nucleophile, so that's a simple addition, right?
Yeah.
Okay.
Yeah, careful on carbon counts here. It's not just a benzene, it's a benzyl. So I have the extra carbon.
Mm-hmm.
Yeah, I'm thinking a common mistake I would see a student make would be if they had the benzene connecting directly but, and losing that carbon. So be careful. Carbon count. I'm gonna sound like a broken record, but I'm gonna say carbon count until the end of the semester.
The double bond stays, right?
You missed a double bond, Professor.
Oh, yeah. Where did I put the double bond at? I'm missing double bonds in this one, right?
Yeah.
Where did it go?
To the right.
Right. Yeah.
Carbon 12.
No, to the left. To the left.
My other,
yeah.
Other right. Okay.
Position.
All right.
It's hard to see.
Can you not see it?
It was just small.
Oh. All right.
Play it.
I'm almost out of paper. What am I going to do? Oh, I have another ream. I've already gone through like a ream and a half of paper since we've been doing this online teaching. I only brought 2 home from work, so I might have to go to the store soon. Does Hammond know if we can go to school and get supplies if you run out? Wondering if you know.
I was aware we could not go back for any reason.
Yeah, I had a few things I needed for my office. Like I'm doing Lewis structures at 103 next week, and I don't have any model kits at home. So
if you run really fast, they'll never catch you.
The security won't stop you if you can let yourself in with your own card key. But if they have to let you in, you have to have written permission from the governor.
From the governor?
From the governor.
Oh, wow.
Just like type up a letter. From there. Are we doing a Claisen? Is that
possibly?
I'll tell you if we're doing a Claisen. I'm just kidding. This is like Dykman. Like the example from Dykman.
I'm going straight to the hard problem.
And it's your reagents.
I skipped the simpler one. We're doing right to the hard one. All right, the reagents we use here is step 1 is NaOET. Just like we saw before earlier today, you want to match whatever these are. So if an acyl substitution happens, it doesn't change the outcome. And then the HCl quench at the end.
So this is the molecular Claisen,
Correct.
which is also the Deichmann.
Yes. You know, it's like this person literally just iterated on Clayton's work and then put his own name on it. It reminds me of the Henderson-Hasselbalch equation. You cover that at 122.
Yeah, the HH equation, yeah.
Yeah, so it's literally just if you take the pKa expression and then negative log both sides and then rearrange, that's Henderson-Hasselbalch. So he just did some algebra.
So when you have, okay, let me ask you this. Since you have esters on both sides, you're going to have to use the alpha carbon to attack the carbonyl. Does it matter which side you use?
In this case, yes.
Oh, because is it going to be the whole like least versus most substituted situation?
Yeah.
Okay. So then I would assume that it's going to be the alpha carbon on the right attacking the carbonyl instead of the left.
Well, did we show enolates from this base going less or more substituted?
More substituted.
Yeah.
So then it would be that one.
Yeah.
Okay.
Professor Mord, I think you're going to need one more carbon.
Yeah, this is a four-member ring. I was like, oh.
Yeah. We can let's do it anyway. Let's do it anyway.
Okay, so then you are going to
Can we do mechanism with this one?
What was that question?
Can we do mechanism with this one?
Yeah, I was kind of
Done
working
any
on that here. So first part here, we form the enolates.
Yeah.
I'm actually going to draw the arrows in right here.
Yeah, deprotonate. Yeah.
And you guys pointed out it's going to make a four-membered ring, so this probably wouldn't work very well. But I want to do it anyway. So then intramolecular attack. And you got to think about where the connections are going to be. The connection is going to be from alpha carbon here to this carbonyl. That's 1, 2, 3, 4. So then we're going to have ETO like so.
Oh God, try naming this.
New bond is here.
No, hate that. Well, then we just quench it, right? No? Cool.
So what do I do next?
Is that a plus on your oxygen or a minus? I can't see what that
is. It's a minus.
That's minus.
Could you move the paper a little bit to the left if you don't mind?
Left? Like that?
Yeah. Like.
To the right.
Yeah, to the right. My bad. That's what I meant.
That better?
Yeah, that's way better.
And now it's quenching with acid, right?
There's one more step first.
Is that a double bond with the red or is that a single bond?
Single.
Because, oh, okay. I thought you were
highlighting the new bond, that's all.
Okay.
Don't you kick off the OET?
Yep.
Yeah.
Yeah, so remember, this is an acyl substitution with the enolate nucleophile.
That's why I was like, was that a double bond? Because that won't work.
So if you're actually following the mechanism, typically what we show is we'll show another mole of base deprotonate another alpha carbon, and then the HCl gets rid of that. Well, I'm just going to stop it here at this one. We have the product now. Should we do more of these types or more Claisen?
Sure.
All right. All right, we can do that one. Then we can see. Try these two. So what's going to happen with this first part here?
Reduction.
No, that's deprotonating the alpha carbon.
Mm-hmm.
Yeah.
And then what does that do?
To make an enolate, you mean?
Yep. So. Okay. And then what does that react with?
Itself.
Yep. So just for the sake of practice, let's do the mechanism here for this one too. So this is going to go out and attack. It's going to attack itself. What's up, Tristan? Are you okay? What's up? You want to do some OChem? Come check out Daddy's drawings. My students love them. Yeah, we'll come back to this one here and then just work on this one. Don't you want to start working on this stuff? Yeah, so basically you're going to get whatever, at this alpha carbon, you're going to have this attached. Like that. I'm highlighting the new bond.
Mm-hmm.
And then you can show that. I'll usually redraw it as a straight chain at the end after I get the drawing worked out. And then you can show the deprotonation, reprotonation with the HCl, but that's the final product.
So we don't do saponification and decarboxylation for this product?
No.
Okay.
You can't do the decarboxylation anyway because the ketones is too far away. right? No, wait, is that right?
Right,
No, it's far enough away. It's right there.
Mhm.
Yeah, but typically they'll show that with acid and heat for that last part.
Oh, okay.
Would it work if the alpha carbon is a tertiary carbon?
If the alpha carbon is tertiary,
Yeah.
I don't think so because you don't have a proton to deprotonate for the enolate step. So you won't be able to make this if it was tertiary.
If it's tertiary, have another hydrogen there, no?
Yeah.
So right.
Yeah, you're
So
saying
right
that,
now it's a secondary, no?
Yeah. So if we had so typically this is shown with 2 H's here.
Yeah. So what if there's only 1 hydrogen there?
Does Hammond have an answer to that question?
Yeah, you will compete to turning your ester into an amide.
Oh.
Because the LDA is so bulky, he'll hate trying to pull a tertiary hydrogen off. So if he'll either do nothing or he'll attack the ester himself.
Okay. Yeah, it's on the book. It says if it's tertiary, it wouldn't work.
Yeah, it doesn't work tertiary because you're doing bulky against bulky. Yeah.
Okay. Okay, cool.
All right. Well, I think I'm actually going to stop recording. We can keep working, but I want to stop recording because this is getting kind of long. So I think there's enough content for the class. But I'm going to hit stop on the recording right now.
Are we going to do this again Thursday, or are we having like an actual lecture Thursday, or is that